Uh, Hi everyone. Are you able to hear me? Okay, cool. So I welcome you to this session. So these sessions are being taken by us to help you with your GATE subjects. So today I will be assisting you with uh, some topics in the electronic devices subject, and today we will be talking mostly about the So today I'll be talking mostly about the Fermi-Dirac statistics and the density of states. Okay, so those who are joining late, it is really inconvenient for me to again and then click in on admit. So from next time onwards, please join within the first 5 minutes so that I can focus on the session. Okay, so uh, today I will be talking about density of states. So, anybody has any idea? You might have uh, read what is density of states. You can open your mic and speak up. Anyone?
Of atoms.
Atoms. Okay. So, how do you? Okay. Someone has written probability of finding electrons in an energy band. Okay. So, uh, that is fine. Megha. Sorry guys, I lost power. I'll just reconnect through my mobile internet. Really sorry for that. Uh, I'm so sorry. I lost power, so my internet may not be that great, but I hope you can see. So I'll be writing slowly on the iPad so it is visible. So density of states. So density. Okay. So it has two terms: density and states. So states is the available seats for the electron if we talk about density of states of conduction band. And density just means per unit volume. Yeah, Bharat, I am recording, and yeah, I will share the recorded links later. Okay. Okay, so you might have, I'm not sure, but you might have seen the uh, this kind of diagram, right? uh, EK diagram, if you know. So for silicon I'm drawing something like this. So this is the EV, this is the conduction band minima EC, and this is the band gap, right? So this this EK diagram comes from solving the Schrodinger equation. But I will not get into that how do we get this, but let just assume that this is something energy versus momentum diagram that we get for uh, a silicon lattice after solving the Schrodinger equation. So here for the top band the minimum is the minimum of the conduction band, and the top of the band below is the maximum of the valence band, and in between, as we know, is the forbidden energy gap, that is the band gap of silicon, and it should be 1.12 electron volt for silicon, right? So uh, is this fine? Like, have you guys seen this kind of energy band diagram before? Okay. Yeah, so can you guys please keep on responding, or let me know anytime if you do not understand, because I cannot hear you or see you. Okay. Okay, fine. Jayesh, do you have a problem?
No, sir.
Okay, you were putting thumbs down, so I thought you might not be understanding something. Okay. Anyways, so to find the current, what we are interested in is number of electrons or holes. But the information that we currently have is not sufficient to find how many number of electrons or holes that we have. So we need to know two things. First is available energy states and how they are distributed. This is actually density of states. And the second thing that we want to know is the probability that these states are occupied, right? So let us go to the first thing now, density of states. The second thing will be driven by the Fermi Dirac statistics. So we will talk more about it later, but let us continue for now. So let us look at the density of states first. So density of states, let us call it d of E. So density of states is a function of energy. It is given by 1 upon 2 pi square. For silicon I'm writing 2 m star by h cross square to power 3 by 2 under root E minus EC. Now again, the derivation for this is not important, but if required, I will share with you a document where you can refer like where this comes from. But for now, let us just take it as it is. And we what is important for us to know is that the density of states is, if I want to draw DE versus E.
Electrons.
Sorry, uh,
It's function of electrons.
it's function of electrons. Did you say?
So
Uh, what do you mean by it is function of electrons?
with respect to the variation of density of electrons, we decide about the density.
That is not true actually. Density of states are the available states for electrons to occupy. So density will all the state the available states. So consider this like a classroom. In a classroom, you have, let's say, 100 chairs. Now those all 100 chairs are unoccupied and empty. So they are those 100 chairs are always there. But if you will go and sit on which chair, that depends on you. If you are the electron, right? So that classroom, the number of chairs in the classroom are not dependent on the number of electrons. So that statement is incorrect, that density of states depends on electrons. It is actually a material property, and it does not depend on electrons. It is just the available spaces for the electron to come and occupy. Okay. Okay, so we can write this as, if I consider all this as constant k, so I can see dE is equals to k times root of E minus EC. So it is a square root function of energy. E is energy here. Okay, so if I draw this, it is something like this, right? Okay, if I put it E minus EC maybe, or I can also draw it like this. Sorry, I'll also draw it like this. I want to say EC minimum from the minimum of conduction band, and if the energy is going up in this direction, so the density is increasing, right? It is increasing like this. This is what DOS is increasing with energy. So the diagram that we drew earlier, if we refer back to it, it was something like this. I'll draw it like this. So if this is EC minimum, so the density is increasing. So there are more states as we go higher for electrons to occupy. Okay, now this was density of states. The next thing is the Fermi-Dirac statistics. So for Fermi-Dirac, let me write it. So probability function f of E equals to 1 upon 1 plus exponential of E minus EF by KT. Okay, so this is actually probability that a particular electron state is occupied. So how this works is, so if I plot this, right, this function, if I plot f of e versus e, so let us take few cases at t equal to 0, at 0 temperature. So let us say this point is ef. So for energy is greater than ef, if t is 0, so exponential of something positive by 0 will be infinite, right? And e to the power 1 upon e to the power infinity 1 plus e to the power infinity will be 0. So it will be 0 here. And similarly, if for right hand side here, e minus ef will be negative, so 1 upon 1 plus e to the power negative upon 0, 1 upon 1 plus e to the power minus infinity, and this minus infinity will be 0 and it will be 1 only. So this will be 1 here, 1. So this is the function at t equal to 0, and we consider ef, at ef the probability is 1 by 2. So it is 1 and 0 at the same time, we consider it to be 1 by 2. Now when we increase temperature, what happens is we get this, right? T greater than 0. So as temperature increases, there is more and more probability that for as we go E greater than EF, we can still find electrons. Probability of finding electrons is finite, right? So this is, so basically the Fermi-Dirac statistics just dictates the probability of finding the electrons, and density of states is the available spaces for the electrons. Now to find the number of electrons, what we need is, so number of electrons could be given by the first of all the density, that is d of E, into the probability of finding the electrons there, right? Available spaces for electrons, electron, and probability of finding the electron. Okay, so this is fine. So now, okay, so let's just put the values in here. It was 1 upon 2 pi square 2 m star by h cross, sorry, h cross square power 3 by 2 under root e minus ec, and fe is 1 upon 1 plus e to the power e minus ec by kt, and this needs to be integrated from minimum of ec to ec minimum to ec top. We want to find the number of electrons in conduction band, right? So we will integrate it from top of the conduction band, sorry, minimum of the conduction band to top of the conduction band. So ec minimum, we generally, if we see the band diagram, you might have seen this, so ec ev, so for minimum I'll just write it as ec, and for top I will change it to infinity, right? So when we integrate this, I'm not going to integrate it right now, I'll just write the result. So n of e we get is some constant times e to the power minus ec minus ef by kt, and this nc is effective density of states. okay, in conduction band. So this is one of the important results that we may need for solving the questions. So no need to remember all of the derivation, but it is good to know, but you should know this. Okay, and similarly for holes, let me write it maybe as P of E equals to NV e to the power, sorry, EV minus EF by KT. NV is effective density of states in valence band. Okay, so and if I just write the values of NC and NV, just a second, this is also important. So NC is 2 m star KT by 2 pi h cross square power 3 by 2, and NV is 2, okay, 2 is outside, sorry, 2 m star KT by 2 pi h cross square 3 by 2. So this is mass for this, it will mass of electrons, will be mass of holes, effective mass of electrons and holes respectively. Okay, so so let me call it the intrinsic carrier concentration, right? N0 equals to this, P0 equals to this. So if we do N0 times P0, N0 P0 equals to NC NV e to the power, if we look at it, minus EC plus EF, right, minus EC plus EF, and plus EV minus EF by KT. So EF and EF will cancel. We will have N0 P0 equals to NC NV e to the power EV minus EC by KT. That is, what is EV minus EC? 0 P0 equals to NC NV e to the power minus EG by KT. EC minus EV is the band gap, right? EG. Are you guys following? Okay, great. So for intrinsic, we define now the intrinsic carrier concentration. So for an intrinsic semiconductor, we know that for an intrinsic semiconductor, N0 equals to P0 equals to, let's call it intrinsic concentration Ni, which is typically 10 to the power 10 per centimeter cube for silicon. Okay, so I'll replace N0 P0 by Ni. So now I get Ni square equals to Nc Nv to the power minus Eg by Kt. Okay, so this is Ni. So one thing we know now is N0 P0 equals to Ni square. Very important relation. So for intrinsic semiconductors. Okay, so now what we will do is okay, so we know n0 equals to nc e to the power minus ec minus ef by kt, and p0 equals to nv e to the power minus ef minus ec by kt. Okay, and for okay, so here, from here we can write nc equals to n0 times e to power uh, ec minus ef by kt, and nv equals to p0 times e to power ef minus ev by kt. So I have just rearranged here and here. So yeah, this is this. Now if I put this nc and nv in these here, I would get something like this. So n0 would be, okay, so this n0 p0 I will replace by ni, ni, ni. So n0 we can write now is uh, ni e to the power ec minus ef by kt into, so we just wrote for nc, now e to the power minus ec minus ef by kt. So which is if I try to solve it, okay, this won't give me anything, these will cancel, and 0 is equals to ni simply. Yeah, so this is ni, this is also ni. So if I let us take the ratio of these two, nc and nv. So if I write nc by nv, I will get okay, let us not take ratio of nc and nv, let us take the ratio of n0 and p0. So let me copy this here. Okay, okay, both are ni, that is fine. So if I take the ratio of n0 by p0, I will get 1, right, because both are ni. So this will be actually nc by nv e to power minus ec minus ef by kt, and e to power minus ef minus ec by kt. So this is nc by nv e to the power minus, okay, minus ec plus ef minus ef minus ev, it's ev, sorry. Yeah, so this will go up plus ef minus ev, so ev whole upon kt. So this is equals to 1. So nc by nv e to the power minus of ec plus ev plus 2ef whole upon kt is 1. Okay, so I can break it down now. nc by nv e to the power minus ec plus EV by KT to e to the power 2 EF by KT. Okay, so equals to 1. Okay, so fine. So if I put e power minus EC plus EV by KT e to the power 2 EF by KT equals to NV by NC. Now let us take log on both sides. So it will be minus, right, minus EC plus EV by KT plus 2 EF by KT equals to ln of NV by NC. Okay, so if I want to write, just want to write in terms of EF. So 2EF by KT equals to EC minus EV by KT, sorry, EC plus EV by KT plus ln NV by NC. So KT, if I EF equals to EC plus EV by 2 plus KT by 2 ln NV by NC. And if I want to write it, I can write as EF equals to EC plus EV by 2 plus, sorry, now I can write minus KT by 2 ln NC by NV. If I write it NC by NV instead of NV by NC. Okay, so what we know, if EC EV, so the middle of that will be EI, that is the intrinsic uh, level of the semiconductor, so I can replace it by EI. EI is basically EG by 2, right? So EF equals to EI minus KT by 2 ln NC by NV. So this is another important relation that we may need. Okay. Till here, is there any issue? Is there any doubt? Are you guys following? Okay. So this was the case for intrinsic semiconductor. So now what will happen in extrinsic semiconductor? So what is an extrinsic semiconductor? Where we dope the semiconductor. So for n-type, we dope by pentavalent impurities, that are phosphorus, arsenic, etc. For p-type, we dope by group the trivalent impurity, that are like boron. Yeah, I remember boron only. Aluminum maybe. Generally boron. Okay. So how does this work is, so now we know that we have EC, EV. So let's say we want to make it n-type. So how it works is, for the impurities, so basically we have the silicon atoms, right? Si, Si, Si. So let us say if we dope it by arsenic, so this As will replace this atom and it will will bring another extra additional electron with it, right, which it can donate. And okay, so this will create another donor level here. Let us call it ED, right? So this donor level has a lot of electrons. So as more and more arsenics will bring additional electrons, and these electrons can easily go into conduction band, right? They can go into valence band also if there are spaces. So let us say earlier, okay, if there is no ED, then the electron concentration here is the intrinsic equilibrium concentration N0 or Ni, and here it is P0. Now if I have a donor level ED, their electrons can now go, so it can become N0 plus Nd, right? Some electrons may also go to the valence band and may reduce P0 to something P0 minus X, but let us just consider for now N0 plus Nd. And similarly, if there are EV, EC and acceptor states. So acceptor states will have holes which would be filled by electrons from the valence band. So which will leave holes here. So holes earlier were P0, they will become P0 plus Na. Okay, so this is simplistic. So earlier we had the relation N0 P0 equals to Ni square. So this still holds, it was for intrinsic. For let's say N type extrinsic, the relation would become N0 plus Nd into P0 equals to Ni square. So N0 will actually, so earlier N0 plus Nd will almost be Nd. So N0 we know, right? N0 was equal to Ni equals to 10 to power 10 range. And doping we generally have Nd is minimum we have 10 to power 15. Maximum it can go up to 10 to power 21 or 22. So this is very large compared to this, so it can be approximated like this. So we can have the whole n is equals to Nd, and we can write it as Nd P0 equals to Ni square. So P0 is equals to Ni square by Nd. Similarly, if we have p-type doping, we can have N0 equals to Ni square by Na. Okay, so these are also important relations. Okay. So one more thing that we need to see is, before we go to some questions, is for intrinsic we had N0 equals to Ni exponential of Ef minus Ei by Kt, right? So where did we see this? Okay, I have not written it, but yeah, this will be there also. N0 equals to Ni e to the power Ef minus Ei by Kt, P0 equal to Ni e to the power Ei minus Ef by Kt. These are also important relations. So for intrinsic we had this, So if we write EF minus EI equals to KT ln N0 by Ni. So for intrinsic, basically N0 equals to Ni. That is why this term ln Ni by Ni is 0 and EF equals to EI. But for extrinsic, we have EF minus EI equals to KT ln. Now instead of N0 we have ND here, right? ND by Ni. So EF equals to EI plus KT ln ND by Ni. We have this here. Okay. And if we want to write it, we can also write it like maybe for this was for N type. For P type, EF equals to EI minus KT ln Na by Ni. P type. Okay. Okay, so I guess this is enough theoretical background. Now we can solve some questions based on this. So just give me a minute, I'll share some questions. Sorry. Okay. Okay, so this question was in GATE 2020. So let us see what this question is and which of the above theoretical background or theoretical formulas that we just solved will help us to solve this. So the question says single crystal intrinsic semiconductor. So whatever we know intrinsic, temperature 300, effective density of states for holes is twice the that of electrons. So we need to pay the detail, the attention at the details in the language. So effective density of states of holes is twice that of electrons. So effective density of states is Nc or Nv. Now it says for holes is twice that of electrons. So Nv is equals to 2 times Nc. This is the given information. And the intrinsic Fermi level is shifted from mid band gap energy by. Okay. So the given information we have is T equals to 300 Kelvin. Nv is 2 times of Nc. And this thermal voltage is nothing but Vt is Kt by Q, which is 26 millivolt. Okay. So how do you solve it? So can anyone first try it, then I'll solve it. I want you guys to first try it. It's a simple question, and one of the formulas that we used will be used here. Harshini, you wanted me to repeat something, but sorry, I missed your message. Can you please repeat which step were you talking about? Okay. So please attempt this question. Uh, yeah, I will share the recording as well as the slides. So let me tell you what you can use. The formula that we may use here is this relation that we just found, right? This relation can be used to uh, solve this question. Very easy, right? So I'll write the relation also. We use is EF equals to EI minus KT by 2 ln NC by NV. This is the relation that we will use. Okay, so basically what it is asking me, Fermi level shifted from the mid band gap energy level. Mid band gap energy level is EI. So basically it is asking us EF minus EI is what, right? So EF minus EI equals to minus KT by 2 ln NC by NV equals to minus KT by 2 ln 1 by 2, right? NV is 2 times NC. So which will on solving give us, so it will be minus 0.026 upon 2 ln 1 by 2. It will be 9.01 into 10 to the power minus 3 EF minus EI, which will be 9.01 milli electron volts. This is EF minus EI. So let me see what you have guys answered. A. What is A? So A is not the answer, B is the answer. You may have been missing this 1 by 2 factor. So is this question clear, or do you guys need me to repeat it? Salomon says it's clear. Manasa probably has some problem with it. Manasa, what is the okay? Manasa, what is the problem you are facing? Any part you did not understand? What are you writing? I cannot understand. Curly null. Okay. KT by 2 is not 0.026. Actually, KT by Q is equals to 0.026. Okay, just write KT is electron volts. KT by Q. Okay, fine. Let us see. K is what? Boltzmann constant. And what is its value? I'll search its value. I don't remember. It is 1.38 10 to the power minus 23. Joule per Kelvin. Temperature is 300. KT will be something 1.38 into 10 to the power minus 23 into 300 joule per Kelvin into Kelvin. So Kelvin cancel in joule. Now I want to know it in electron volts. So for electron volt I will divide it by Q. So KT by Q will give me 1.38 into 10 to the power minus 23 into 300 upon 1.6 into 10 to the power minus 19 electron charge. This will give me 0.026 electron volts. So KT by Q is 0.026 or 26 millivolt. Sorry, milli electron volts. Right? So KT by 2 is not, KT by Q is, or in electron volts. Kt in electron volts is 26 millielectron volts. So here let me reiterate. Here this Kt will be replaced by 0.026. Here we have done 0.0626 by 2. Manasa, is it okay? Curly, I don't know why you have this name. Okay. Manasa, do you have any problem? Okay. Prince, I am from IIT Gandhinagar. Okay, so let us move on to the next question then. Okay, so you guys try to solve it first. Again, it is very easy to solve. Just first try to see what they're asking and what information do you have. So let us note the given things first. It is doped now, doped silicon with boron, so that is p type. To sum this concentration, intrinsic characteristic concentration, this is Ni. Kt by q is, they were given to be 25, so they have given Kt by q is 25 millivolts, so Kt is 25 milli electron volt, and doping is given. Na is 4 into 10 to the power 17 per centimeter cube. Ni is 1.5 into 10 to the power 10. Compared to undoped silicon, the Fermi level of doped silicon goes by what? So they are again asking Ef minus Ei is what? Similar question to previous one, but now doped. Okay, before that, Prince, again let me reiterate. So I did this Kt by Q just to change this to change the unit to from joules to electron volt. Both are the units of energy only, right? So generally what we do is, when Kt by Q we do, it is generally the answer is in volts. But if I just take, let's say, if I just embed this in the Boltzmann constant itself, if I write here, I had written the Boltzmann constant to be 1.38 into 10 to the power minus 23 joule per Kelvin. But let's say if I want to write it something into electron volts per Kelvin, both are the units of energy, right? Then just by Kt I'll get 0.026 electron volt per Kelvin. Electron volt and volts are interchangeable as we seem fit. Prince, do you still have a confusion in this? Okay. So now solve this question. Very simple. Very similar to the last one that we solved. So what we'd be using here is this relation, this one, right, for the doped semiconductor. So let me write the relation also. Ef equals to Ei minus Kt ln Na by Ni. This is the relation, right? I forgot. Okay. here you can directly replace kt by 0.0225. Here given 25, so we'll use 25. Okay, so let us try to solve it. EF minus EI equals to minus KT ln NA by NI equals to 0.026 ln NA is 4 into 10 to the power 17 divided by 1.5 into 10 to the power 10. So this is minus of 0.427 electron volts, EF minus EI. So EF goes down by 0.427 electron volt, which is option C. My answer C is correct, goes down. So this is, you don't need to even solve this to answer like goes down or up. Down or up you can know even by just admiring the band diagrams, right? EC, EV. When it is intrinsic, EI and EF both coincide. N type, EC, sorry, EV it is EV, and P type, EC, EV, and EI, EI. In N type, EF is closer to EC. In P type, EF is closer to EV. This you always remember, because when you are, why it is happening, when you are doping in N type, what happens, you are adding more electrons in the conduction band. So the Fermi level goes upwards, right? The probability of finding the electrons goes higher near the conduction band. So is this clear, this question?
Yes, sir.
Okay, great. So I have one more question. This is a very simple question. So you see, from this topic, the questions in GATE are very simple, but there are a lot of questions like this. Some questions are already solved on the GATE portal. I'm here. I will be solving those which have not been solved previously by other scholars. So, but you see, all of these questions are very simple based on only just a few formulas. So solve this one now. So we know n into p is equals to ni square, right? Here n we can approximate as nd, which is 2.25 into 10 to the power 15. So we already know n0 is 2.25 into 10 to the power 15 per centimeter cube. So one of answer would be one of C or D. Okay. Now we have to find P0. So P0 will be Ni square by Nd, which is 1.5 into 10 to the power 10 whole square. Koteshwar Yadav is joining when the session is going to end. Okay. Nd is 2.25 into 10 to the power 15. So actually 1.5 square is 2.25 only, so it is 2.25 into 10 to the power 20 by 2.25 into 10 to the power 15. So P0 is equals to 1 into 10 to the power 5 per centimeter cube. So the answer is D. Very easy, right? So this is a very scoring part, and I think just in 1 hour you can now solve any question related to this topic at least, and easily score 1 or 2 marks. And I think in GATE 2023 last year, I think there were 3 questions in GATE from this part. So it is very scoring and easy. Okay, any doubts here? Okay, so this is all from my side for today. If you have any doubts, please ask, else let us close this session and we will meet next week. I will share the recording as well as the slides on the portal. It will be uploaded. Okay, alright guys, thank you. See you next week. If you have any issues, you can also contact me at om.maheshwari at iitgm.ac.in. Okay, this is my email. I have written it in chat also. Manoj, where can we access? It is there on the GATE portal. I think it will be shared to you by email also if you have subscribed to the GATE ECE portal. But it will be somewhere there on the portal. I'm not sure exactly where, but somewhere there on the portal itself. The live session recordings as well as the solutions to these questions. Not uploading, Koteshwar. It will be uploaded, not if not today, within this week at least. If not, you can just email me. I will upload it on my YouTube channel. You can see it there. Okay? Okay then. See you guys.
Thank you, sir.
Thank you. It will be named by my name only. You can email me, Koteshwar, if you have any problem. Okay. Bye.